Howdy and welcome back. So let's talk about searching, but before we do, let's consider what we just did for the minimum and maximum value. By the binary search tree property, we knew that if we were looking for the minimum valued node within our binary search tree, all we had to do was step as far left as we possibly could. We didn't even have to inspect the actual key values of the nodes that we were stepping over to get to that location. For the maximum key valued node within our binary search tree, all we had to do is step as far right as possible. Because based on the binary search tree property, we knew that the node with the largest key value would be placed as far right as we possibly could walk. So again, we didn't even have to explore or look at the key values of each node that we were going across in order to isolate the minimum or maximum valued keyed node within our binary search tree. Searching, we're going to have to do just that. We're going to have to search. If you think about it, what we're looking for is a node with a specific key value. So if we start at the root, let's say we have, 20 up here, and let's say that's like 10, that's, 30. If we start here and we're looking for 10, some sort of comparison is going to happen, right? Because we've looked at this node's key, first one within our kind of the nodes we'll look at, and it's not 10. Okay, so unlike a linked list, we can't just move to the next node. We're at a branch point, so we have to determine, do we go left or do we go right? Well, this tree's organized, and again, based on the binary search tree property. If the key that we're looking for is less than the key of the node we're currently visiting, we will step left. I'm like looking at the left, did I say right? So if the key value is, so if the node that we're looking for has a key value less than the node we've currently visited, we are going to step left and arrive at the node with 10. If the node we were looking for had a key value greater than or equal to that of the node we were currently visiting, we'd move to the right. I hope I didn't confuse you all with that. But again, just the binary search tree property, right? If X is some node and Y is to its left, Y is going to have a key value less than that of X's. If we have some node Z, and Z is to the, it's ugly, Z is to the right of X, guess what? Z's key value is going to be greater than or equal to that of X. So cool. Let's move forward. So searching. We often need to search for data within our binary search tree, right? It's holding some sort of collection of objects, and we're probably storing those objects in a collection with the idea that we want to retrieve them later. So searching can be accomplished in one of kind of two ways. It can be accomplished through a recursive algorithm that can actually be enrolled into an iterative solution. So we'll have two options here at hand. We can either search for a node with a particular key value recursively, or we could do so iteratively. There's obviously some trade-offs in the one you pick, but we're not going to worry about that just right now. So our search process is going to have to make decisions at branch points with respect to the binary search tree property. If Y is a node in the left subtree of X, then Y's key is less than X's key. If Y is a node in the right subtree of X, then Y's key is going to be greater than or equal to that of X. So let's look at our recursive solution. And before I even look at the code, let's go ahead and say this. We're going to start from the root. So if we look at tree search here, we can see we're going to take some sort of binary tree node object, and it's going to be called current node within the scope of this function and some sort of key value, right? Let's assume we're starting at the root and we're looking for 12. Okay, so this is the recursive solution here. So we'll have tree search, and I'm showing the stack right here, and I'm just going to put in parentheses the invocation of that particular function. So we launch up an activation records push to the stack for our visit to the node containing the key value of 20. First thing we're probably going to want to do is check whether or not we've arrived at the node we're looking for. So if current node's equal to null pointer, we'll see here that that's going to be suggest to us or effectively communicate to us that, we've ran into the null pointer somewhere. So the value that we were looking for was not found. In that case, this return statement here would return the null pointer, and the caller could go ahead and check and go, hey, if tree search returns the null pointer, I know that that value was not, a node with that key value was not found in my binary search tree. Okay, so that's kind of the first thing we have to check for here is, okay, like, does the node exist? Is it the one we're looking for? So if current node's equal to the null pointer or the current node's key is equal to the key we're searching for, we're going to go ahead and return the address to current node. Now notice in this case, the root's key is not 12 and current node is not pointing to the null pointer. So we need to make a decision. Do we go left or do we go right? Well, 12 is less than 20. So we're going to go ahead and step to our left. Notice here we make that comparison on this line. Key, so 12 is less than the current node, 20's key. So we move to the left. Now we go ahead and look. Is current node pointing to the null pointer, or is the current node's key, 8, equal to 12? In this case, no, we have not found what we've looked at, what we're looking for, and we have not exhausted our search at this point. So we have to do a comparison to determine which way we're walking. Is the key value 12 less than the current node's key value, 8? No. So we're not moving left this time. We're moving to the right because the key value we're looking for is greater than the node that we're currently visiting's key value. So we're going to go ahead and step, in this case, right. So now current node is pointing to the node whose key value is 12. Current node's key is not the null pointer, meaning there's still nodes to look at and we could potentially be at the node we're interested in. In this case, the current node's key value, 12, is equal to 12. So we'll go ahead and return the address of this node to the caller. The caller can check that address. If it was null pointer, we would know that we did not find the node with a key value of 12 within our tree. However, because we got a valid address back, we know that a node with the key value of 12 was found. Okay, here is going to be the iterative solution to this. So what we see on the left here is a recap of what we've seen before. What we're seeing on the right here is going to be our algorithm. So let's go ahead and look at this. So instead of checking for the base condition, we're going to set up a while loop here, which is essentially going to say, while there are still nodes to look at and while we haven't found what we're looking for, we're going to take some steps in the right direction towards where, should the node that with the key value of interest that we're looking for exist, we'll find it. And if not, we'll exhaust our search. So in this case, let's go ahead and I'm going to assume here, this could really be any node within our tree. I'm going to call it root, so the root of where we're beginning this search from. So I'll go ahead and say here, current node is going to get initialized with that initial starting point where we'll begin our algorithm from. Let's assume that the node with the key value of 20 is passed in as the location where we will begin our iterative tree search at. So we have this set up. So at this point, we're looking for the node with the key value of 12. We look at the while state conditional. The current node is not equal to null pointer, and the current node's key, 20, is not equal to 12. So in that case, the statement's true. We're jumping into the body. If the key is less than the current node's key, so 12 is less than 20, we're going to move left. Otherwise, we'll move right. In this case, the key that we're looking for is less than the current node's key, so we're moving left. So here we are. We're now updated that current node pointer to point to the node with the key value of 8. Okay, let's go back up and evaluate our conditional statement here. Is current node the null pointer? No, it's not. Is current node's key 12? No, it's not. So we need to keep moving. We haven't exhausted our search, so there's still more nodes we can look through, and we haven't found what we're looking for. So in this case, is the key that of the node we're looking for less than that of the current node's key? No, 12 is greater than 8. So guess what? In this case, we're going to step right. So now current node is going to point to the node whose key value is 12. So have we exhausted our search? No, we haven't, because current node's not pointing to the null pointer, which would have happened had we traversed through a leave or a node with one child that did not have a subtree in the direction that we were supposed to take. Okay, so now we haven't exhausted it. Next is we need to check whether the current key is not equal to the key of interest. In this case, they are equal. So this conditional is not satisfied. Therefore, we will not execute the body. So we're down here. And guess what we do? We simply return the address to the node whose key value is 12. Now, had we returned null pointer, that would have communicated to the caller that we did not find what we were looking for. But here, because a valid address was returned, the caller would know that, hey, this tree search iterative function found the node with the key value that I was interested in. So with that in mind, we're going to go ahead and move on to this idea of successor. So if we were looking for, if we're at some sort of node in the tree, where is the node whose key value comes directly after it located? Think about that for a second. All right,